All right. Well, thank you very much, Brett. Um, really appreciate the opportunity to speak today and appreciate the work of the lead class for their initiative in putting this together. It's making the most of trying circumstances. So definitely appreciate that. I'm also grateful for help I've gotten from several people at SIMS and NSSL. I was at Hazardous Weather Testbed in 2019, and there were some really cool things that came out of that. And that's actually what set the wheels in motion for my talk today. So I originally delivered this at the BOECHO workshop early last month, which now seems about a year ago, but here is most of it in the same form, although I may actually have a little bit of extra material if things work out that kind of goes in line with what I'm going to try to cover today. So you should see a slide now that's called the challenge. And so this kind of lays out what the problem is. We know velocity data or storm relative velocity interrogation is a critical part of diagnosing severe storms. And we know the data can be complex and critical features can kind of be hard to discern sometimes. And this especially is the case when your flow gets highly unbalanced. And so our typical go-to source is radial velocity couplets, but we also look at mid and low level convergence signatures as well as upper level divergence as well. So, excuse me, so this is going to start with some conceptual models to lay the foundation. And what we'll do is try to figure out how to sort of model those mesovortex circulations with QLCSs. And in doing this, we'll use the familiar combined Rankine vortex and show how that relates to azimuthal shear, also known as NROT and GR2. And then what we'll do is go into the less familiar concepts of radial convergence and its divergent shear properties. That's a product that I'll talk a little bit more about. And then finally, this is kind of a little more esoteric, but very interesting and may have some applications in the future, is something called velocity gradient, which incorporates azimuthal shear and divergent shear. And then we'll also see how these products help with identifying unbalanced flow regimes that matter the most with QLCS and mesovortex surges. So hopefully at the end, I got some time to show you something that happened this morning that's rather relevant. Excuse me. So first of all, let's start with radial velocity. So here's your typical radial velocity couplet. The radar is located towards the bottom of the figure. I'm using Cartesian coordinates, so you can think of the y direction as range from the radar there at the bottom, and x direction corresponds to your azimuth angle. So inbounds and outbounds, I've gotten green and pink. And I'm hoping these colors work for those of you with red-green color blindness. I'd be very interested here if that's the case. You know, just let me know offline if you want. But I ran it through a color tester on the web, and it seemed to stand out pretty well. So hopefully that's the case for those of you who do have red-green color blindness. So let's go on to the next slide. So what I've done here is this is a radial velocity depiction of a combined Rankine vortex model. So what we're seeing is increasing radius from the circulation center. We got a linear increase of rotational velocity out to a specified distance. So imagine that like a rotating cylinder. And then beyond that, the rotational velocity is going to decay as a function of 1 over radius. So that's kind of why they call it the combined Rankine vortex. You're combining those two approximations. So the radius where this transition occurs is where ROT V, and therefore the inbound outbound V is the greatest. So you see a R sub max that refers to that. The overlaid trace I've got there, what that's really plotting is the inbound outbound velocity with respect to azimuth angle. And so the horizontal dashed line, you can imagine that is the cross section that's being taken, and that would be corresponding to a 0 outbound or inbound, which is why you've got the line crossing at 0 in the middle where there's no rotational velocity. All right, so going on to the next slide, this kind of breaks it down a little bit more. So if you look closely at the sloping line, you can imagine really that the slope of the trace is equivalent to azimuthal shear because it's the change of velocity, inbound or outbound, with respect to x. And so what we see within the Rankine vortex is a constant positive slope. And that sort of makes sense because the vorticity is constant, the rotation is constant, and we know that from school that anytime you got a solid body rotation like a cylinder, that it's actually going to be proportional or actually equivalent to 2 times the angular momentum. But, and this is a big but, the assumption breaks down in the presence of unbalanced flow. So the times we really care most about is when you really can't make the solid body rotation assumption anymore. So looking at that a little more closely, what we really want to do, and then is focus not just what on the inbound outbound is, but what's the actual shear. And so the way you can do that again is by focusing on the slope. So we've got a positive slope within the rotating cylinder at constant positive values. But then if you look closely, just beyond the radius of maximum inbound and outbound, you actually start to see slopes that are negative. So that's kind of interesting, and we'll talk a little bit more about that. So the largest magnitude of negative slopes are highlighted with those stars there. Okay, so now what we're going to do is azimuthal shear is basically measuring shear across these azimuth. And what I did here is I applied a Gaussian smoother that's going to give the resulting trace if we use that same horizontal cross section as before. So putting it another way, AzShear is the differential radial velocity with respect to azimuth. And this is precisely what NROT or normalized rotation in GR2 analyst does as well. So now what you should see, horizontal line, or excuse me, horizontal line, first of all, the negative values are the blue. Okay, I kind of skipped ahead there. And then the next thing I want you to notice is azimuthal shear is actually 0 where the maximum inbound and outbounds occur. So just kind of keep that in mind. We'll see some examples of why that matters. This could be actually a very good way of indicating where the strongest winds are, as it turns out. Next, I'll just say at the very top part there, the reason this is rounded is because even though it is a solid body rotation and you would expect that to be a constant horizontal line, it's because we're basically doing like a running smooth, right? I mean, a Gaussian smoother is essentially like kind of like a running average type of thing. Takes out some of the noise. So what does this look like? If we now just plot the azimuthal shear with that theoretical curve, what we get is positive in this case is red and negative is blue and 0 is black. And the things I want you to notice is, first of all, not surprising, the azimuthal shear is maximized at the circulation center. But more interesting and less intuitive is positive AzShear is flanked on both sides by less strong negative azimuthal shear. And that transition, as I mentioned before, where it goes from positive to negative actually corresponds to the maximum tangential velocity. And we see, I strongly encourage you to look in NROT because you see cases like this all the time. So for example, this was out of the hazardous weather test bed. You know, case after case, you would see a circulation positive shear that was flanked on both sides by negative. So forgive the color table, but there's a better alternative to this that I'll talk about a little later. Okay, so this is a way of representing balanced versus sheared flow. So what I did here is I'm trying to simulate on the road side what would happen if you had like kind of a rear inflow jet or a rear flank downdraft or that type of thing. And on the left is your more balanced flow. So this is just basically a way of looking at inbound, outbound velocities, where in this figure the radar is on the bottom there to show you what the orientation is. Now, if we convert that to azimuthal shear, it goes from a symmetrical pattern to something that is not balanced. So you've got more of a prominent blue, more of a prominent negative shear with a positive shear that's probably just as strong, if not stronger. And then if you look closely, you see the blue on the other side is a little less strong. So this goes from basically a balance looking to more of a pole where you got positive next to negative. And we see plenty of examples of this as well. One thing I should note is when it comes to azimuthal shear, the direction you are relative to the radar doesn't matter, because all you're really doing is looking at the change in radial velocity with respect to azimuth. So at the time I gave this talk, this was right after the Nashville tornado, and I was trying to show some examples of how this works pretty well. Now, this is obviously a supercell case here, but what I want you to notice basically is how we've got a transition from what's more or less a symmetrical looking thing, red with blue on each side, to something that's more of a dipole, and that precedes the tornado report. So that's probably associated with an RFD, with the surge, with imbalanced flow. So takeaway so far. AzShear is between max and in and out, and 0 is going to be where you've actually got your strongest inbounds or outbounds, and negative matters a lot too, as we'll talk about a little more. So a lot of this is somewhat familiar, but now we're going to go into less familiar territory where we're looking at convergence components. We don't have that luxury in radar, but as you can imagine, it matters quite a bit. So this is kind of the model I used, where convergence is maximized at the radius of maximum rotation, just kind of an arbitrary model here. And so if we look at that from a radar perspective, this is what you would see. Not surprisingly, you would get inbound farther away and outbound closer in. And so also not surprisingly, if you combine the two, you're going to get your, convergent rotation type of thing. I know this is familiar to most of you. So now what we're going to do, though, is kind of look a little more closely at the interplay of azimuthal shear, divergence shear, et cetera, and we'll break it down a little bit. So what I want you to focus on is these areas right here. Okay, so here's what we got. We're going to start with storm relative velocity on the left-hand side here. So the radar is located to the right of these pictures, okay? And so here we've got an inbound that's flanked on both sides by relative outbounds. Now, if we look at azimuthal shear, again, remember this is kind of like NROT. What we see is we've got maximum cyclonic and maximum anticyclonic that corresponds with that interface that you see between the inbounds and the outbounds. And then if we finally look at velocity gradient and put those two together, I haven't really explained velocity gradient, so let me do that right now. What it's doing, it's taking the sum of the square root of the sum of the squares of azimuthal shear and divergent shear. The reason that matters is because negative values, as I've been saying, matters a lot. And you don't want to just take an average. Taking a square root of something squared is going to make sure that the magnitudes are preserved. And that's what's really useful about that right here. Okay, so now what we'll do is we're going to start with storm relative velocity. We're going to talk about divergent shear. So this is kind of the unfamiliar one. So now what I want you to look at is we've got an area where there's convergence on the right, which is closer to the radar, and divergence on the left, which is farther away from the radar. And so now if we look at the divergent shear component, I flipped the colors here because convergence is more interesting to us. I made it red. You'll notice that you've got this essentially like a couplet of divergent shear. And when you put it together here, now you've got another dipole. So the net result, interestingly, is that you've got like a velocity gradient circle where you've got a dipole in the azimuthal shear and you've also got a dipole in the divergent shear, something you're not usually going to see very often, but it is a rather interesting thing. Okay, so now what I'm going to do is kind of talk about how this all comes together. So what I want you to notice is, first of all, this is a feature following zoom here. This was a storm back in 2008 that kind of piqued my interest in the whole azimuthal shear / NROT couplets. So you'll see a line going by, a yellow line that's associated with a very strong QLCS mesovortex that produced like EF1 types of damage. And what I want you to notice as we run through the loop again and again is the interplay between the azimuthal shear, which is on the upper left, and again, red is positive shear, and then look on the upper middle part where you've got divergent shear, red is convergence. And you'll notice that very often you'll get a nice combination between the two. Also, what you'll sometimes see is even though the azimuthal shear may get weaker with time, the divergent shear still indicates strong convergence and a good possibility for things to redevelop again. Also, if you look very closely, it's interesting because it's fortuitous how this storm basically went right across Detroit's radar. And so you can see how in velocity gradient on the upper right, you'll notice that the values are rather impressive, both to the north and the south of the radar as it passes over, even though the values of azimuthal shear are negative, to the south. So it does a great job of picking up boundaries. You'll see there's little filaments behind the boundary itself that point into the boundary that show where surges are going on. It's just a really neat way of representing what's going on. And so this is kind of what I was saying before, where if you go back and forth, you can see how azimuthal shear is negative south of the radar, but velocity gradient is still very very relevant and important and noticeable. So again, this talk happened right after the Nashville tornado. So I thought this was a really good illustration of how you can really visualize this. It is my hope that just like we can view azimuthal shear / NROT and GR2 analysts, maybe one of these days we'll be able to look at div shear in a similar way. Okay, so this is extremely fortuitous. Looks like I'm still okay on time, about 16 minutes, so I'm almost done. But this happened this morning. This was a reported tornado, and so where I've got the red dot there here, and I'll show it real quickly. The red dot is where there was actually a report of a tornado. Now I'm moving the cheese on you a little bit here. I'm using a different color table. The upper left is NROT, and the color table is on the left there. So basically the difference is that the blue is still negative values, positive values go from warm to hot. This table was created by my MIC Dan Cobb. It's a really nice curve, I think, and if you're interested in having a copy, let me know. But this is a great example of a QLCS surge and a possible tornado. So I'm actually looking at the 0.9 degree slice to approximate about 5,000 feet above radar level. And this lines up nicely with WHIP training on mesovortex genesis height. And it's also a really good argument for looking at Merle instead of sails, because the time gaps here between the 0.9 cuts are over 7 minutes. So I think it would have been better served doing some kind of Merle strategy, because the action was really up above the 0.5. So as I mentioned before, upper left is NROT / AzShear, same thing. Upper right is reflectivity. Lower right is spectrum width. I hope Ray Wolf's on the call, because I know that's kind of a nod in his direction because he's a fan, justifiably so, of looking at spectrum width. And lower left is storm relative velocity. So I want you to note as I step through this, the developing NROT couplet. So you'll see a blue next to hot colors, indicating increasingly unbalanced flow and a developing surge that precedes the tornado genesis. The other thing I want you to notice is the damage apparently occurs in the middle of the NROT couplet associated with the surge itself. And then finally, what I want you to notice is the velocity is going to show a radial acceleration, which could likely have been resolved with div shear. So here we go. This is the first frame. Then this is the next. Hopefully y'all can see the red dot there. So we see a nice QLCS strongly convergent, strongly sheared feature to the south of where the report's going to occur. Now, jumping ahead 7+ minutes, notice how suddenly we've got a very well-defined type of couplet here. There's the blue, and there's the negative, and there's the positive, the hot colors. So it does an amazingly good job there, and it all makes sense associated with a surge. And notice also it's the damage is right between where the couplet occurs. And then if we go a little farther, you notice a general weakening. But I would argue that it's very easy to get a feel for what's going on with this type of stuff. What I was mentioning before is that you do see some radial accelerations that I think would have been very interested to take a look at with the velocity products. And maybe that's something I'll run a case on a little later. So with that in mind, if there is a case that you have that you're interested in, I do have a way of running it. I may not be able to get to it right away, but if there's any kind of QLCS related thing that you want to see some of those velocity products in action, please let me know. And that ends my presentation. Thank you very much.
Well, thank you, TJ.